This presentation, Group E8, will be presenting to you a desalination facility located in Saudi Arabia. This presentation will include the electrical systems and other domains, possibly for parts that include the water intake, pre-treatment, reverse osmosis, capacitive deionization, lighting, and environmental, temperature, heating, and humidity.
You can see the 4 diagrams in my PowerPoint containing power generation, power conversion, and MATLAB. Photovoltaic power generation is suitable for large water intake systems because of the large volume of water we have to feed. My main design idea was how to improve the efficiency of the centrifugal pump. I used a rectifier to rectify the three-phase AC power to reduce output ripple. The power consumption is evenly distributed to improve system reliability, and the BLDC motor is controlled by Hall signals to issue accurate control and efficient drive. The disadvantage is that the energy consumption is high, as a DC to AC to DC is used.
Here is my model for the pre-treatment facility. In this presentation, I will be explaining the models that I have used and why I have used them exactly. Before I begin, my aim was to create a DC motor which acts as a rotating motor in a flocculator tank. I first started off by making the power generation. For the power generation, I decided to use 2 solar cells, and in those 2 solar cells, I have an irradiance of 1000 common 3. And the reason I decided to use 2 solar cells as well is because I want to create a DC voltage for my system. Once I've got a DC voltage, I can now move on to the conversion, and for this, I decided to use a buck converter. What will happen is I will have an input DC voltage going into the buck converter, and the output voltage will be stepped down. And the reason for this is so that I don't use too much voltage when I try to supply voltage to the load. Now that I've stepped down the output voltage, for the load, I decided to make a simple DC motor and then measure the RPM that is generated. Once all this was connected, I now moved on to my control systems. And for the control systems, I have an irradiance of 1000. I also have the control system for the buck converter, which also contains the reference voltage. And I also have an R load, which is connected to the piecewise constant resistor. Thank you for listening.
In order to accomplish reverse osmosis, a motor is required to push the water through the membrane. I powered this motor by using solar panels generated in the power generation subsystem. Then the DC power from there goes into a 3-phase DC to AC inverter, and then this goes to 2 sets of 3-phase step-up transformers, and then finally to the squirrel cage motor. I used a 3-phase signal because this increases the power efficiency, and so does using 2 series transformers. And finally, I regulated the power by I regulated the voltage output of the power generation by using a control system, and I regulate the speed by on the motor by using another control system. And on the top left hand corner, you will find power and efficiency calculators for each part.
For capacitive deionization, the process is powered by solar panels, which of the output voltage is around 220 watts. The 220 watts gets converted to 400 watts using boost converters. From here, the voltage can be applied to other higher demand equipment as the voltage output is around 400 watts. After the boost converter stage, the voltage gets stepped down to 220 watts, which is converted into DC. Which is converted into AC using inverters. The inverters are controlled using two signals. The inverted DC signal gets rectified back to DC using a full bridge rectifier. After the full bridge rectifier, the output voltage is around 70 watts DC, which is still too high for the final load. Therefore, the voltage is halved to around 30 watts, which is much more suitable for the load. Also, the current is reduced down to 350 milliamperes, which combined with the 30 watts DC is absolutely appropriate to supply the load and therefore the process.
Hello, here's the environment simulation part. The left big graph shows a DC voltage source generated by three solar panels so that to make the circuit more realistic. Then an average value DC to DC converter is connected, which is for maximizing the power generation efficiency and maintain the stability and accuracy of the output voltage. After that, two motors are connected to the converter, which shows in the subsystem, and they are in the same structure but has different parameter. Motors are operating the daily consumption for two systems. So one motor is present temperature and heating control system, and the other one is present humidity control system. The upper graphics represent the power in and power out. They are fluctuate at the beginning of the diagram. After that, the power will change to a stable value. In the lower graph shows the efficiency of this environmental system. It has the same situation with the power graph. At the beginning happened fluctuation, then it began the stable value. The value of efficiency is 78.75%. That is it for my part. Thank you for listening. Hello, here's the environment simulation part. The left big graph shows a DC voltage source generated by three solar panels so that to make the circuit more realistic. Then an average value DC to DC converter is connected, which is for maximizing the power generation efficiency and maintain the stability and accuracy of the output voltage. After that, two motors are connected to the converter, which shows in the subsystem, and they are in the same structure but has different